Hi boys, today we're going to be looking at conditional probability and doing a test for independence. Now, conditional probability refers to the probability that one thing happened given that another has already happened. And we denote it as A given B, so just a vertical line. Formulaically, this is the probability that A and B have both happened, or what we call the intersection of A and B, divided by the probability of B, which we can see there. Now this obviously requires that the probability of B not be equal to 0, as in that case we'd have a division of 0. And in that case, we're also able to rearrange the formula to find any of the other subjects. That is, if we were given the probability of A given B, and we're given the probability of B, and wanted to find out what's the probability of A and B, we can just imagine, like any other formula, multiplying both sides by the probability of B. And this is true when also finding the probability of B. If we wanted to, we could rearrange the formula into this. So it's really important when we approach any of these problems to list all the information we've been given in the question and substitute what's appropriate in order to solve what we want. Sometimes, in order to find one of these variables, we might have to draw out a probability tree or a tree diagram, and other times it might actually be in the question. So here we've got quite a routine problem. It says, given that the two events A and B, the probability of A is equal to 0.6. So we might just make a note of that. That's one of the pieces of information we have. The other being that the probability of B equals 0.3, and the probability for B given A is 0.1. So the first thing I might do before I do anything is just list what we have. That is, the probability of A is 0.6, the probability of B is 0.3, and the probability of B given A is equal to 0.1. Now the question asks us to find the probability of A and B, or A intersection B. Now what we have that might allow us to relate to this is the probability of A given B, but all we have is the probability of B given A. So before we can proceed, we might look to relate what's information that we have with what we'd like to have. So we'll start with what we know about the probability of B given A. Well, the formula here would state that the probability of B given A is equal to the probability of A intersection B. Remember, this is the same as B intersection A, divided by the probability of A, the second term. Now, we don't have A and B. We do have probability of A, and we do have the probability of B given A. So we can try and substitute these in. 0.1 is equal to the probability of A and B divided by 0.6, which we also know from the question. So we can rearrange in order to find the probability of both A and B happening. If we multiply both sides by 0.6, that's like saying 0.1, 1 over 10, times 0.6, 6 over 10, is 6 over 100. So we end up with 0.06 is equal to the probability of A and B. Now remember, we're actually after, that does actually answer the probability of A and B, but we're after part B here, which is the probability of A given B. And quite frequently, we may not be given this question in part A, part B. It may have just given us this information and asked us to find the probability of A given B. And this would require us to do exactly the same thing we've done here, find a piece that we need, A intersection B, and sub it into a formula. So we'll rearrange this to say this was part A, but for part B, we've got our formula. The probability of A given B is equal to the probability of A intersection B over probability of B, which in this case is 0.06, we found from the previous part, divided by 0.3. It's a bit like saying 6 over 100 divided by 30 over 100, so that the hundreds would cancel. We get 6 over 30, which is 1/5. So we can evaluate that to be 1/5 or 20%. Conditional probability is also more frequently presented to us as a worded problem. Now, looking at this question in front of us, there's a fair bit of information which needs to be broken down. It says in a certain town, the probability that it rains on Monday is 0.21. So there's a good thing that we need, is that it rains on Monday. That's one of the events. The context is that it's 0.21% chance. So let's start with the fact that the probability of it raining on Monday is 0.21. Now it says here that if it rains on Monday, then the probability that it rains on Tuesday is 0.83. So here, the bit of context is that it's already rained on Monday, then the probability of it raining on Tuesday is 0.83. So we know that to be the probability that it will rain on Tuesday given Monday is 0.83. So not quite as clear here. It's not that it's the probability of it raining on Tuesday, it's the probability that it rains on Tuesday given it rained on Monday is equal to 0.03. It says if it does not rain on Monday, then the probability of rain on Tuesday is 0.3. So we might think here the probability, whoops, let's just change that to a pen. The probability of T given it didn't rain on Monday is equal to 0.3. Now, this information is not quite as clear as formulaic as we'd like it to be, and it's not going to be as simple a case as simply subbing it into a formula. So again, the context, if it does not rain on Monday, so if m dash or m complement, then the probability of rain on Tuesday is 0.3. The question itself is relatively simple. It's saying find the probability that it rains on both Monday and Tuesday. Now step one in a problem like this is going to ensure that we do a tree diagram. This will really allow us to find things like the probability of it not raining on Monday and likely what would happen after that. So if we started with there being rain on Monday or it not raining on Monday, we know the probability from above is 0.21, which means that the probability of it not raining on Monday must be 0.79. Now on Monday it will either rain or it won't, so the total probability there has to be 100, or 1. Now, we know that the probability of Tuesday raining being the next day, so either it will rain on Tuesday or it won't. Again, either it will rain on Tuesday or it won't. The probability of Tuesday raining given Monday happen was 0.83, which yields 0.17, being that it won't. Likewise, we know T given M complement is 0.3, which we read from the question, which yields a remaining 0.7 for the possibility of not raining on Monday and then not raining on Tuesday. Now the question said that it would rain on both Monday and Tuesday. And in order to find the probability in a problem like this, we know that it would be the probability of raining on Monday times the probability of raining on Tuesday. So that is the probability of Monday and Tuesday raining is 0.21 times 0.83. Now we can use a calculator to find there that the probability is 0.1743. And so for part A, the probability that it rains on both Monday and Tuesday, we would look to recontextualise our answer here and say the probability that it rains on Monday and Tuesday is 0.1743. And the second part of the question is just that it rains on Tuesday. Now this could be a little bit difficult because there are in fact two options where this is the case. If we go back to our tree diagram, it could rain on Monday and then on Tuesday, but it could not rain on Monday and then also rain on Tuesday. So there's two options here that we'd have to test. There's the probability of both Tuesday and Monday occurring, which we've already found, and the probability of Tuesday and not Monday occurring. And so for this here being part A, just flick back to a pen, this being part B, we know that we can just add these two possibilities together. So Monday, Tuesday, and not Monday, but yes for Tuesday. Just there. So we've got from the previous question the probability of Tuesday being 0.1743, which was that top tree, plus, now we've got 0.79 times 0.3. And if we use a calculator to sum those two things together, we end up with 0.4113. Again, we would contextualise this as the probability of it raining on Tuesday. So the probability it rains on Tuesday is 0.4113. Another option for solving these is to utilise the law of total probability. Now this seems a little bit complicated, or like there's a lot of pieces to the puzzle, but there really isn't, and it makes sense. So it says here that the probability of A happening is equal to the probability of A given B times the probability of B, plus the probability of A given B dash times the probability of B dash. But you might notice that if we look at the first section here, A given B times B, well, we knew that as just a rearranging of the probability of A and B. And we might extend our understanding here to see that the second part, probability of A given B didn't happen, times the probability that B didn't happen, is just the probability of A and B not. So this makes a fair bit of sense. The probability that A happens is equal to the probability of A and B plus the probability of A and B not. This might make more sense in a Venn diagram where we've got A and B. Well, the probability of A and B is easy enough. It's in here. And the probability of A and not B means that it has to be everything that is here. And we can see visually that that's obviously the probability of A. Now this next question has quite a bit to it, and the events are not as simple as Monday followed by Tuesday. But it's pretty much the same approach. It says Adrienne, Regan and Michael are doing the dishes. Since Adrienne is the oldest, she washes the dishes 40% of the time. Regan and Michael each wash the dish 30% of the time. So we can imagine that we have the probability of Adrienne washing dishes equal to 0.4, the probability that Michael, which is equal to the probability of Regan washing the dishes, is 0.3. Now it says when Adrienne washes the dishes, the probability of at least one dish being broken is 0.01. When Regan washes, the probability is 0.02, and when Michael washes, the probability is 0.03. So looking at what our two events are, it's first of all a matter of seeing who washed the dishes, and second of all, the probability that a dish is broken, or at least one dish is being broken. That's the second event here. So it might need another tree diagram to work this out. We start with either Adrienne, Regan, Michael, and either the dish will break or not. So it will break or it won't, and it will break or not. Now it says here that the probability when Adrienne washes is 0.01. So Adrienne, we knew, had a 40% chance, and now 0.01, which means that there's a 0.99% chance that she does not break a dish. Regan was 0.3 and Michael was 0.3. However, it says here that when Regan washes, the probability is 0.02 that something will break, which leaves 0.98. And for Michael, it's 0.03, which leaves 0.97. Now it says that their parents don't know who is washing the dishes one particular night. That really is just there to show you that these are, could be anything. If they knew that it was going to be Adrienne, then obviously we know the chance of it being broken. But the question says, what is the probability that at least one dish will be broken? So we're after here, what is the probability of B? Now, we could look at the probability of anything happening there as the probability of B given A, or B given R, or B given M. And so if we're finding one or the other, again, this is just a case of summing up the probabilities in the tree for which there is one broken dish. So there's A followed by B, there's R followed by B, or there's M followed by B. And we need to sum up these three events. So we've got the probability of Adrienne first. So we've got, imagine this as AB, or that top row, is equal to 0.4 times 0.01. We've got RB, which equals 0.3 times 0.02, and we've got MB, which equals 0.3 times 0.03. Now we use a calculator to find these out. The first one you might see by hand is just it's actually 0.004. The next one is 0.006. And the last one is 0.009. Now if we add all of these again, this is saying that we've got to add them all because they all represent a chance that something could be broken. We end up with 0.19. 0.019, I mean to say, sorry. Now part B says, given that at least one dish is broken, what is the probability that the person washing was Michael? And this is a slightly more complicated question. But if we think of it formulaically, we could say that part B, excuse me, I'll write that out in red, is equal to the probability that Michael will wash given the dish was already broken. Now we know that, and I'm running out of room here, so we'll just zoom out a little bit. the probability of M and B divided by the probability of B. And all this information we found in the last question, because the probability of M and B was just Michael followed by B, so 0.3 times 0.03, which ended up being 0.009. And the probability of B happening was 0.019. Now, if we use a calculator to divide this, we might get a decimal answer, or we could just see that this is equal to 9/19. Sometimes we're also given conditional probability questions in the form of a table of events that have already occurred. This might represent large survey results, or it might be recordings of populations throughout the year. Any context, it always really changes. Now it says at the top here that as part of an evaluation of the school canteen, all students at a secondary college, years 10, 11, 12, were asked to rate the canteen as poor, good or excellent. The results are shown in the table below. What is the probability that a student chosen at random from this college is in year 12? Well, here we're not really worried about two of the events happening, i.e. they're in year 12 and also they rated this one. All we're after is in year 12. So the only thing we have to look at here is that there are 80 students in year 12 and 400 students in total. So part A is really just a matter of saying the probability that a student will be in year 12 is equal to 80 over 400, which we may look at as 8 over 40, and that works out to be 1/5 or 20%. Now part B, we've got two parameters here. It says that it is in year 12 and rates the canteen as excellent. Well, if they are in year 12 and they rate the canteen as excellent, this is also only one parameter. So in year 12 and rates the canteen as excellent means that there are 35 students out of 400 that did that. And so again, we just equate this to what we read in the table, which is 35 over 400. While this can be a little bit confusing, it's really very much like the example of saying what's the probability of something being a diamond and a queen in a deck of cards, and the only option there being the queen of diamonds. So the answer is 1 in 52. Very, very similar case. We know that there are 35 year 12s who said it was excellent, and there are 400, so it's a simple 35 over 400, which simplifies to 7 over 80. Now part C says that the student is in year 12 given that they rate the canteen as excellent. Now here's where we stray a little, but not much. If they're in year 12, well, there's 80 students in year 12, and given that they rate the canteen as excellent, there are 160 students who do that, we can see here. But we know that only 35 of the year 12s rated it as excellent. Now this says is in year 12 given that they rate the canteen as excellent. We can imagine that they've rated the canteen as excellent, so this is the only thing that we're looking at. And how many students there were in year 12? Well, it's 35 out of 160. So this is equal to 35 out of 160. And if we divide by 5, we can simplify that to 7 over 32. The last one says that they rate the canteen as excellent given that they are in year 12. So now one way to think of that is if we're saying given that they're in year 12, given that we're only talking about these 80 students, how many of those students rate the canteen as excellent? And we can see that there are only 35 of those students. So for part D, we say that there are 35 out of 80. So again, the given that they are in year 12 means that we're only looking at that red column. Now 35 out of 80 also simplifies to 7 over 16. The last law that we're having a look at is the law of independence. Now, we know that if the probability of A given B is equal to the probability of A, then that means that B must have had no effect. If, think of this like flipping a coin, the fact that I flipped a heads in one trial means nothing about the chance of getting a heads in the next trial. It's still 50%. So if we can prove that the probability of A given B is equal to the probability of A, and if we can also prove that the probability of B given A is equal to the probability of B, then it's true that the probability of A intersection B will be equal to the probability of A times the probability of B. Now this is really useful because it makes some of our work much easier. For instance, in example 5, the probability that Monica remembers to do her homework is 0.7. So I know that I've got a probable chance of 0.7, and I know that the thing I'm talking about is Monica does her homework. So let's say here the probability of Monica doing her homework is 0.7. It says while the probability that Patrick remembers to do his homework is 0.4. So the thing that we're talking about is that Patrick remembers to do his homework, and the context here is 0.4. So the probability of Patrick doing his homework is 0.4. Now the question here gives us a big piece or big advantage where it says if these events are independent. Now if these events are independent, so I don't have to test that, what is the probability that both will do their homework? Well, this is an easy one. Because they're independent, and let's just write that out with a pen, the probability that they'll both do their homework is 0.7 times 0.4. Think of that like 7 over 10 times 4 over 10, which equals 28 over 100, or 0.028. Now, this is really, I suppose, a lesson in reading the question carefully, because we wouldn't know that if we didn't pick up on the sentence, if these events are independent. And as I'm looking at that, I've just realised I've accidentally written an extra 0. I meant to write 0.28, sorry. Now, what is the probability that Monica will do her homework, but Patrick forgets? Now remember, the word but is a logical connective that works exactly the same way as the word and when we're talking in mathematics. So the probability that Monica will do her homework and Patrick will forget is like saying the probability that Monica and Patrick complement. Now we know that if probability of Patrick is 0.4, then Patrick complement must be 0.6, and we have the equation 0.7 times 0.6. Now 0.7 times 0.6, you might think of that as 7 times 6 is 42 over 100, so we get 0.42 as the answer.